Hey everybody, and welcome to this video on solving one-step multiplicative equations. So let's get the show on the road. Alright, consider the equation 2m equals 4, which we're also representing with our scale model. Now we have two of these m blocks on one side of the scale and 4 kilograms on the other. As we discussed before, we can add or subtract the same amount of weight to both sides of the scale, and the scale will remain balanced. This is the same as saying that we can add or subtract the same number to both sides of this equation, and the equation will remain balanced, or true. But there are some other things that we can do as well. For instance, looking at the scale, I claim that we could double the weight on each side of the scale, and it would remain balanced. Since the weight to begin is the same, doubling the weight on each side is like adding the same amount of weight to both sides, so the scale should remain balanced. Heck, we could have taken our original equation and we could have tripled the amount of weight on both sides. We could have taken our original equation and quadrupled the amount of weight on both sides. Heck, we could have taken our original equation and multiplied the weight on both sides of the scale by 6. And each of these times, the scale and equation remain balanced. In fact, I think we could have multiplied the weight on each side of the scale by whatever we wanted, as long as we multiplied each side by the same number, and the scale would have remained balanced. Well, what does this mean for an equation? It means that we can multiply both sides of an equation by whatever number we want, as long as it's the same number to both sides, and the equation will remain balanced, or true. But what about dividing? Let's start with the equation 6a equals 12, which we've also modeled using our scale. Now my claim is, if the left-hand side of the scale is exactly the same as the right-hand side of the scale, then if we take half of the weight on the left, it should be exactly equal to half of the weight on the right. Which means if we take away half of the a's on the left-hand side and half of the 1's on the right-hand side, the scale should remain balanced. In theory, we could have started with our original situation, and we can say that if the left side of the scale weighs exactly the same as the right side of the scale, then 1/3 of the left side of the scale is the same as 1/3 of the right side of the scale. So if we have only 1/3 the amount of a's on the left and 1/3 the amount of 1's on the right, the scale should remain balanced. Equivalently, starting with our original situation, if the a's on the left weigh as much as the 1's on the right, then 2/3 of the a's on the left should weigh the same as 2/3 of the 1's on the right. Or even, starting at our original situation, if all those a's on the left weigh the same as all those 1's on the right, then 1/6 of those a's on the left should equal 1/6 of those 1's on the right. In fact, I claim that we could divide the weight on both sides of the scale by whatever we wanted, as long as we did it to both sides, and the scale would remain balanced. What does this mean for an equation? It means we can divide both sides of an equation by whatever number we want, as long as it's the same number on both sides, and the equation will remain balanced, or true. Alright, last thing. Consider this equation. -3y equals -9. Now this one's really interesting to model using our scale. On the left-hand side of the scale, we have 3 balloons, each pulling up with a weight of y kilograms, for a grand total of a weight of -3y kilograms. On the right-hand side, we've got 9 balloons pulling up on the scale with a weight of 9 kilograms, for a total weight of -9 kilograms. Now here's my claim. If 3y kilograms pulling up is the same as 9 kilograms pulling up, then it must be that 3y kilograms pushing down is the same as 9 kilograms pushing down. And of course, our scale will remain balanced. That is, with a scale, as long as it's balanced, you can change it from both sides pushing down to both sides pulling up, and vice versa, and the scale will remain balanced. What does this mean for an equation? It means that given an equation, you can multiply both sides of the equation by -1, and the equation will remain balanced, or true. So in total, what we've just uncovered is something called the multiplicative property of equality, which says that, given an equation, we can multiply or divide both sides of the equation by the same number, positive or negative, and the equation will remain balanced or true. All right, let's try using this property to actually solve some equations. For instance, 3k equals 12. Now, we don't want to know what 3k equals, we want to know what k equals. So what we need to do to isolate k is we need to find 1/3 of 3k. So looking at the equation, we can either divide both sides by 3, or we can multiply both sides by 1/3. Looking at the scale, all we need to do is keep 1/3 of the k's on the left side of the scale and 1/3 of the ones on the right-hand side of the scale. And both with the equation and the scale, we find k equals 4. Let's revisit this equation one more time. Now there may have been another way to get k on one side of this equation. For instance, if we subtracted 2k from 3k, we'd have 1k left over, and we'd have k by itself on one side of the equation. So let's go ahead and subtract 2k from both sides of the equation. Now, while we do have k by itself on one side of the equation, we wouldn't say that it's adequately isolated. Why? Because on the other side of the equation, we still have that unknown variable k in there. So even though we have k equals, we don't know what number this is because we still don't know what k is. So in this case, adding or subtracting k's is not going to be good enough to adequately isolate our variable. And in general, when we have these types of equations, where we have some number times our variable equals just another number, adding or subtracting isn't going to cut it. We're going to have to multiply or divide. All right, let's try another one. How about 1/4 m equals 5? Well, we don't want to know what 1/4 of m is. We want to know what m is. But we know that m is going to be 4 times 1/4 of m. So if we look at the equation and we multiply both sides of this equation by 4, we'll end up with m equals 20, the solution to our equation. Looking at the scale, on the right-hand side, we've got 5 kilogram units. On the left-hand side, you can see what a full-size m block would be, but we only have 1/4 of that. In order to get a full m block, we need to take 4 of these quarter m blocks. So if we're going to multiply the weight on the left-hand side of this scale by 4, we need to multiply the weight on the right-hand side of the scale by 4 as well. And again, we see that m equals 20. All right, one more. How about -2h equals -5? Now again, we don't want to know what -2 times h is. We want to know what h is. So what can we multiply or divide both sides of this equation by so we have just an h? Well, I claim we could divide both sides of the equation by -2, and the -2 and -2 will cancel out, and we'll have just an h. Or we can multiply both sides of the equation by -1/2, because -1/2 and -2 are multiplicative inverses, and they'll multiply to 1, leaving just h again. And in both cases, we get h equals 5/2, or 2.5 if you want to use a decimal. Looking at the scale, in this case, we've got 2 h balloons, each pulling up with h kilograms of force, and we've got 5 balloons on the right pulling up each with 1 kilogram of force, for a grand total of -5 kilograms. Well, if they're both pulling up with the same amount of force, then it must be that 2 kilograms of force pushing down would be the same as 5 kilograms of force pushing down. So we see that 2 H blocks weigh the same amount as 5 kilograms. But of course, we want to know how much 1 H block weighs. So we want half of the H blocks on the left and half of the 1 blocks on the right. Of course, we see that this is going to involve a fraction of a block here, but that's okay, no problem at all. And again, we see that H is 2.5. Alright, now that we've had ample time to investigate these types of equations using the scale, it's time to try solving some using just the equations. And our general strategy is just to multiply or divide both sides of the equation by whatever we need to in order to isolate our variable. And I urge you, we're going to walk through all of these, but why don't for each of these you pause the video, give it a try, and then hear me walk you through it. Alright, for the first one, negative 6w equals 14. We got two options of how to handle this. The first is to divide both sides of the equation by negative 6. Negative 6 divided by negative 6 is 1, so they cancel out, and you're left with just w equals negative 14 over 6. And in general, whenever you can, please go ahead and simplify your fraction. And I'll be honest, I personally prefer improper fractions way over mixed numbers. So just a heads up. Our other option was to multiply both sides of the equation by negative 1/6. Negative 1/6 and negative 6 are multiplicative inverses, they're reciprocals, they multiply to 1, and we get w equals negative 14 over 6 again. Alright, how about negative 8/3 m equals 6? There are two strategies for how to take care of this one as well, but they're slightly different for what we did from the last example. The first strategy is to multiply both sides of the equation by negative 3/8. Negative 3/8 and negative 8/3 are multiplicative inverses. They multiply to 1, and we get m equals negative 18 over 8, or m equals negative 9 over 4. Now the other way to handle this, if you're not so comfortable with fractions, is to start by clearing those fractions. If we multiply both sides of this equation by just 3, then we don't have any more fractions, and this should be no problem. We just divide both sides of the equation by negative 8. Alright, 4 more practice problems. And they're a little bit different from the ones we've seen, but I'd like you to pause the video, and please try and solve the 4 of them. And when you're done, play the video, and I'll walk you through them. Alright, for this first example, 5g over 9 equals negative 4. The biggest hurdle is to realize that 5g over 9 is the exact same thing as 5/9 g equals negative 4. And once we're here, all we got to do is multiply both sides of the equation by 9/5. 9/5 and 5/9 are multiplicative inverses. They multiply to 1, and we get g equals negative 36 over 5. For our next example, negative 7/9 m equals negative 2/3. Very similarly to the one we just did, we're going to multiply both sides by the multiplicative inverse of negative 7/9, namely negative 9/7. Negative 9/7 and negative 7/9 multiply to 1. We get m all by itself. M equals 18 over 21, or 6 over 7. For our third example, we don't have to, but we might as well simplify 6/10 right away. And from here, we're just going to multiply both sides of the equation by the multiplicative inverse of 3/5, namely 5/3. 5/3 and 3/5 multiply to 1. We get w all by itself, and w equals negative 20 over 3. Our last example, we may think to immediately divide by negative 7, but yeesh, on the right-hand side, 3/4 divided by negative 7, that's a pretty awkward looking fraction, so let's try something different. Well, instead of dividing by negative 7, we could multiply both sides by negative 1/7. Negative 1/7 and negative 7, they're multiplicative inverses. They multiply to 1, we get m by itself equals negative 3 over 28. Alright guys, that's it for this video. I hope you found it helpful, and I hope you enjoyed.